last lecture, we introduced this idea of a confidence interval. So what's a confidence interval? Here's example 1 from our last lecture. In this example, we were after the proportion of the population who would support funding the new CRC library building. And the idea was we can't ask everybody, right? There's just too many people. So instead of asking everybody, we asked a sample of people. Here we asked a sample of 238 people. And from these 238 people, we computed a confidence interval, which was something that looked like this. And what this says is that if we were able to ask everybody, the true proportion should be somewhere between this low number and this high number. That's a confidence interval. In this section, we're going to continue that idea, but instead of talking about confidence intervals for a proportion, we're going to talk about confidence intervals for a mean. And the process is going to be very similar. Step 1, we can't ask, or we can't find the mean from the entire population. There's just too many people, and we can't. So the next best thing is to find the mean from a sample, and that's called finding the point estimate. And the symbol is going to be X bar. That just means that that's the mean that you get from the sample. Step 2, this is where the big difference happens. In the proportion situation, step 2 was to find a Z star based on a confidence level, right? And that refers to this picture. The area in the middle is our confidence level, and we're looking for the 2 Z stars. And this picture is our normal distribution from chapter 7. So I'm going to call this the Z distribution, okay? So it turns out that for the mean situation, the Z distribution doesn't quite work. And we have to use a new distribution called a T distribution. So that's this picture up here. The solid line here, that's our standard normal picture. So the solid line is our Z distribution. The dotted lines are our T distributions. So notice that there's not just a single T distribution, there's a family of T distributions. Actually one for each sample size that we use. And what this picture is showing here is that the dotted line at the bottom, that's a T distribution for a really small sample size, for a sample size of 2 actually. So for a really small sample size, notice that the T distribution differs by a lot from the solid line, which is a Z distribution. But as your sample size gets bigger and bigger, as you use more and more people, the T distribution actually gets closer and closer to the Z distribution. So if you're using a really large sample size, the T distribution and the Z distribution are about the same. But overall, the T distribution is going to give you more accurate answers for the mean situation. So in step 2, instead of finding the Z star, we're going to find the T star. Based on the confidence level. And instead of drawing the Z distribution, we'll draw the T distribution, which for me looks almost exactly the same. But it's a T distribution instead of a Z distribution. And then the confidence level is still the area in the middle. And then our goal here is to find the T stars instead of the Z stars. And then let me tell you the command in R that we'll need. So in the proportion situation, we were finding area to Z, and then the command was qnorm. In this situation, we're looking for area to T, and the command in R is going to be qt. And you feed it the left area. And then something I'm going to call a DF. And DF stands for degrees of freedom. And it's really just the sample size minus 1, n minus 1. And n is our sample size. Step 3, just like in the proportion situation, is to find your margin of error. And then the difference is it's going to be a different formula for means. For the mean situation, the margin of error is going to be T star S over square root of N. And S is our standard deviation. N is our sample size. Same N. So that's an N, same N here. And then once you have your margin of error, step 4 is to construct your interval. In the proportion situation, it was p hat plus or minus the margin of error. Here it's going to be x bar plus or minus the margin of error. And that's the 4-step process for constructing a confidence interval for a mean. Before we move forward, let me say a little bit more about why the z-distribution doesn't quite work for the mean situation. And it really comes down to these formulas from chapter 7. This is the same formula sheet from the end of chapter 7. And these formulas, remember, tell you what mean you should use and what standard deviation you're supposed to use when you're using the normal distribution. And what you should notice here is that, first of all, in our confidence interval situation, we don't know the population proportion, we don't know the population mean, we don't know the population standard deviation. Okay, so we're estimating all of those things using our sample. In the proportion situation, we're estimating the population proportion. And that's it. That's one thing, right? Once we have the population proportion, that tells us the mean, and it also tells us the standard deviation using this big square root formula. So in the proportion situation, we're only estimating one thing, the population proportion, which is different than the mean situation. In the mean situation, we're estimating the population mean, but also the population standard deviation. So we're estimating two things with our sample for the mean situation. Because in the mean situation, the mean and the standard deviation aren't linked together like they are in the proportion situation. Right? In the proportion situation, the mean and the standard deviation is linked using this square root formula. So in the mean situation, since we're estimating two things with our sample, the z-distribution doesn't quite give us the most accurate answers there. Since we'll be dealing with both means and proportion situations in this section, what I want to do on this page is just collect all the formulas that I'll need here. This is going to serve as my cheat sheet for chapter 8. So for confidence intervals, the end product we want is either going to be p hat plus or minus e in the proportion situation, or x bar plus or minus e in the mean situation. First two formulas tell us how to find our margin of error. So these are both formulas for margin of error. The first one with the z star and the p hat, that's for the proportion situation. The second formula with the t star is for the mean situation. The second two formulas, these are for situation before you even do your study, when you're planning the study and deciding how many people to use. In other words, you're trying to find the sample size. The first formula with the p hat and z star, that's for the proportion situation. The second one is for the mean situation. Both of these, all these formulas have either z stars or t stars. So to find z star or t star. they both involve this picture. And it's shaded in the middle. The shaded area is our confidence level. And you're either going to look for the Z stars or T stars, depending on what your formula is requiring. And then to find your Z star, T star, the commands in R, all of these are area to Z or area to T problems, are either going to be QNorm or QT. QNorm is for the Z star situation, and then QT is for finding the T star. And then finally, the last thing I want to put on here, just to be complete, is what happens to the margin of error when you increase or decrease your sample size and when you increase or decrease your confidence level. So effect of sample size. Okay, so if you use a larger sample size, what happens? Larger sample size means the n is bigger. Right? Notice that in both these formulas, the n is on the bottom, right? N is on the denominator. In other words, you're dividing by n. So if you're dividing by a bigger n, overall, you'll get a smaller margin of error. Larger sample size will result in a smaller margin of error, which is the same thing as saying a narrower interval. Which means a smaller sample size should give you a wider interval. And then what's the effect of the confidence level? Confidence level refers to this picture, right? A larger confidence level means that this area is bigger. If this area is bigger, then these Z stars or T stars would have to go out wider. So a larger confidence level will result in a wider interval. Which means the opposite, a smaller confidence level will result in a narrower interval. All right, I'm ready to try some examples now. Example 1. To study the rental market in a city, a housing official surveys a simple random sample of 43 renters and found that the mean rent paid was $940 with a standard deviation of $300. Part A, construct a 91% confidence interval for the mean rent in this city. So the first thing we need to decide is, are we talking about means or are we talking about proportions? So obviously it says mean, right? Construct a confidence interval for a mean. So we want a confidence interval for a mean. Which means our end result, I want an x bar plus or minus e. Which means the first thing I need to do is find x bar. And x bar is the mean from our sample. So what's the mean from our sample? The mean rent paid was $940. So it's $940. Step 2 is to find our critical value. And step 2 involves looking at this picture. Where the area in the middle is our confidence level. And our confidence level we're talking about here is 91%. So 0.91 in the middle. And we're either looking for Z stars or T stars. Because we're talking about means, right, The margin of error formula for mean has a t star, so which means I want to find a t star. And so to find t star, the command in R is going to be qt, left area df. So we're going to do qt, left area df. What's the left area? 0.91 is the area in the middle, right? I want this unshaded part on the left here. So to get that unshaded part on the left, I'm going to first do 1 minus 0.91, which I think is 0.09. That gives me the unshaded part, which is the left and the right together. If I just want the left, divided by 2. So 0.09 divided by 2. 0.045. Okay, that's what you feed into the QT, 0.045. QT requires a DF also. Okay, QT is left area DF. DF is degrees of freedom, which is 1 less than our sample size. Let me interrupt here and tell you where the term degrees of freedom comes from. Say I ask you to give me 5 numbers that have a mean of 20. 1 number, 2 numbers, 3 numbers, 4 numbers, 5 numbers that have a mean of 20. There's many answers here. In other words, you have a lot of freedom in how you choose these numbers. But you actually don't have total freedom. The first number, you have freedom. You can pick any number you want. The second number, you can pick any number you want. The third number, you can pick any number you want. The fourth number, you can pick any number you want. But once you've picked the first 4 numbers, that last number is locked in. There's only one number there that will give you a mean of 20. You can use algebra to find that missing number. So even though you have 5 numbers, 1 less, which is 4, only 4 of them do you have full freedom to choose. And that's where the term degrees of freedom comes from, and that's why it's 1 less than the sample size. Okay, sorry for the interruption. Back to the problem. What is our sample size, and what is 1 less than it? Sample size is 43, so 1 less than that will be 42. All right, so we're going to do QT 0.045, comma 42. QT 0.045, comma 42. Negative 1.735. So that gives us one of the t stars. So one of the t stars is negative 1.735, rounded to 3 decimal places. I expect 2 t stars. So that's the one on the left. The one on the right is going to be positive 1.735. Step 3. Step 3 is to find our margin of error. We're talking about means, so our margin of error is going to be t star s over square root of n. T star is I always use the positive one, so I'm going to use 1.735. S over square root of n. S is our standard deviation. What's our standard deviation? 300 over square root of n. N is our sample size, which is 43. Okay, so in decimals, type that in. 1.735 times fraction 300 over square root of 43. So square root 43. 79.376. Okay, round each intermediate step to 3 decimal places. And then finally, step 4 is to construct your interval. So it's going to be x bar, which is 940, plus or minus our margin of error, 79.376. And then I need to subtract to get my low number and then add to get my high number. So 940 minus 79.376 is 860.624. Low number, and then the high number, 940 plus 79.376. 1019.376. And that's your confidence interval. Part B, interpret your result, and part A in a complete sentence. And so the sentence I want you to write for all of these are, we are, state your confidence level. So in our case, we are 91% confident. That, what are we talking about here? We're talking about the mean rent in this city. We are 91% confident that the mean rent in this city is between 860.624 and 1019.376. Okay, these aren't proportions, so we don't convert these to percentages. So between 860.624 and 1019.376. And what are these supposed to be? These are supposed to be rent, right? So these are actually dollars. Even though we didn't ask everybody, what we're saying here is that if we were able to ask everybody, the mean rent would be somewhere between $860.64 and $1,019.376. And then to answer our question, part C, based on a confidence interval, can you conclude that the mean rent in the city is less than 1,000? All we know is that the true mean rent in the city is somewhere between $860.64 and $1,019.376. Can we say for sure that it's less than 1,000? No, right? It could be as high as 1,019, which is definitely not less than 1,000. This is a no. Part D, if the sample size were 30 rather than 43, would the margin of error be larger or smaller? 30 will be a smaller sample size, right? So if you replace 43 with a 30, you're dividing by a smaller number, which means overall you'll get a bigger number, or a bigger margin of error. It'll be larger. And then if you need to, go back to our cheat sheet, right? 30 will be a smaller sample size. Smaller sample size will result in a wider interval. Wider interval means that the margin of error is larger. So larger. Part E, if the confidence level were 87% rather than 91%, would the margin of error be larger or smaller? Confidence level has to do with this picture. Okay, currently it's 0.91. If it were 87%, if it were 0.87, what happens? So 0.87 would be a smaller confidence level, which means the area would be smaller. If the area is smaller, these t-stars would actually have to go in closer, right, or narrower. So narrower is the same thing as saying a smaller margin of error. It'll be smaller. And if you need to, go back to the cheat sheet. 87% will be a smaller confidence level. Smaller confidence level would be a narrower interval, which is the same thing as saying a smaller margin of error. Example 2. The dean of students at a university wants to estimate the proportion of students who log into Facebook daily. She posed a simple random sample of 200 students, and 134 of them report that they log into Facebook daily. Part A, construct an 86% confidence interval for the proportion of students who log into Facebook daily. First of all, is this a mean question or just a proportion question. It says, find a confidence interval for the proportion. So obviously this is going to be proportions. So our end product, we want a p hat plus or minus the margin of error, which means the first step is to find a p hat. This is the proportion from our sample. So for proportions, you'd actually do have to do a computation, right? So we talked to 200 students, and 134 of them say that they log into Facebook daily. So the proportion from a sample is going to be 134 out of 200, out of the total. Okay, 134 out of 200 is 0.67. Okay, if you need to, round to 3 decimal places at that point. And then step 2. Step 2 involves this picture. And the area in the middle is the confidence level. What's our confidence level here? 86% confident. That's 0.86. And then we're either looking for Z stars or T stars. For the proportional situation, our formula for margin of error has a Z star in it, so we're looking for a Z star. And for Z stars, we do a Q norm left area. Okay, so we're going to do Q norm left area. What's the left area of this picture? 0.86 is the area in the middle. To get the left area, I'm going to first do 1 minus 0.86. 1 minus 0.86 is 0.14. That gets you the unshaded part, which is the left and right together. If I just want the left, divide that by 2. So 0.14 divided by 2. 0.07. Okay, that goes into my Q norm. Q norm doesn't have a DF, so it's just, that's it. Q norm 0.07. Negative 1.476. Okay, that's our left one. The one on the right should be positive, so that's going to be positive 1.476. Step 3. Step 3 is to find our margin of error. So the margin of error for the proportion situation is going to be Z star and then big square root. So Z star is 1.476. I always use the positive one, so 1.476. Big square root, p hat, which is 0.67, parentheses 1 minus p hat, 1 minus 0.67, over n. N is our sample size. How many people did we ask? 200. Okay, type this into my Desmos. 1.476 square root. And then click fraction just to make sure that that fraction is inside that square root. And then on top, 0.67, parentheses 1 minus 0.67 over 200. Okay, make sure the entire fraction is inside the square root. 0.049. And then last step, construct your interval. So in this case, it's going to be p hat, which is 0.67, plus minus the margin of error. 0.049. Subtract to get the low number, and then add to get the high number. 0.67 minus 0.049 is 0.621. 0.67 plus 0.049, 0.719. And that's our confidence interval. Part B, interpret your results in part A in a complete sentence. Same sentence you write on all this. We are, state your confidence level. In our case, it's 86% confident. That, what are we talking about here? We're talking about the proportion of students who log into Facebook daily. So we are 86% confident that the proportion of students who log into Facebook daily is between. Now, because these are proportions, they do represent percentages. So let's convert them to percentages. Between 62.1% and 71.9%. So even though we didn't ask every single student, we're saying here that if we were able to ask every single student, the proportion would be somewhere between 62.1% and 71.9%. And then to answer our questions, part C, based on the confidence interval, can you conclude that more than 60% of students log into Facebook daily? So if all you know is that the true proportion is somewhere between 62.1% and 71.9%, can you say for sure that's more than 60? Yes, right? 62.1 is more than 60, 71.9 is more than 60, which means everything between is also more than 60. This is going to be a yes. Part D, if the confidence level were 96% rather than 86, would the margin of error be larger or smaller? So confidence level has to do with this picture. Right now it's 0.86. If it were 96, so if the area were bigger, then these Z stars would actually have to go out wider. So wider would mean a larger margin of error. Okay, if you need to go to the cheat sheet, 96% means a larger confidence level. So larger confidence level gives you a wider interval, which means the same thing as saying a larger margin of error. Part E, if the sample size were 300 rather than 200, in other words, if you're using a bigger sample size means you are dividing by a bigger number, which means overall you'll get a smaller number. So we should get a smaller margin of error. And if you need to go to your cheat sheet, larger sample size gets you a narrower interval, which is the same thing as saying a smaller margin of error. Example 3. A newspaper wants to predict the outcome of an election by estimating the proportion of voters who support the construction of a mall in Elk Grove. What sample size is needed if the newspaper wants the estimate to be within 3% with 97% confidence? It's asking for the sample size here. So we'll be using one of the sample size formulas on our cheat sheet. Question is, are we talking about proportions or are we talking about means here? It says that they want to estimate the proportion of voters who support the mall, right? Proportion. This is going to be a proportion question. And let me write down the sample size formula for proportions. It's going to be p hat, 1 minus p hat, z star over e squared. So I'll need to find something to plug in for p hat. something to plug in for Z star, and something to plug in for E. Let's start with E. E stands for margin of error. So what margin of error are we shooting for here? It says that they want the estimate to be within 3%. So that phrase, within 3%, they're telling you that they want their estimate to be, that's how close they want their estimate to be. They want to be within 3% of the actual true answer, which means they're telling you right there that they want their plus minus numbers to be 3%, which means that's their margin of error. So the margin of error is going to be 3%. Anytime they give you a percent, you should convert it to a decimal for calculation purposes. 3% as a decimal, move decimal place 2 to the left, that's going to be 0.03. Z star. Z star has to do with this picture. What confidence level are we talking about here? 97% confidence. Okay, that's the shaded area in the middle, the confidence level. And then I want to find the Z star. Okay, Z star, we're going to be doing Q norm, left area. Left area of this picture. 0.97 is the area in the middle. To get the left area, I'm going to first do 1 minus 0.97, which is 0.03. That gives me the unshaded part, which is left and right together. If I just want the left side, divided by 2. 0.03 divided by 2. 0.015. And that's what U-feet are. Now Q norm doesn't require a DF, so that's it. Q norm 0.15. Sorry, Q norm 0.015. That gives me a Z star of negative 2.170. That refers to the left one. The one on the right is going to be positive 2.170. And I'm going to use the positive one for my formula. So positive 2.170. And then the question is, what do you plug in for p hat? Do you plug in 3%? Do you plug in 97%? P hat refers to the proportion that we're interested in. So we're interested in the proportion of voters who support the mall. So do we know the proportion of voters who support the mall? No. Right? So if that's given to you somewhere in the problem, use it. If not, your next best thing to use is 50%. So 50% is going to be 0.50. And so we're going to be doing 0.50, 1 minus 0.50, Z stars 2.170 over E, 0.03 squared. Don't forget the square. Okay, so on Desmos, 0.50, parentheses 1 minus 0.50, 2.170 over 0.03, close parentheses, don't forget the square, 1308, 07028. Okay, we're not done. We're talking about sample size here, so that in other words, how many people should we ask? You can't ask 0.028 people. So how should you round this? And we talked about this in the last lecture. And the answer is you always want to be safe, right? So it's always safest to ask more people. So anytime you have a decimal here, you're always going to bump it up. So we're going to round this up to 1309. Okay, always round up. Example 4. A researcher wants to determine the mean number of hours per week the typical person watches television. How many people are needed to estimate the number of hours people watch television per week within 2 hours with 94% confidence? Results from a previous survey indicate that the number of hours of television watched per week has a standard deviation of 7.5 hours. Okay, it's asking how many people. What's the sample size? So we're looking for sample size again. Question is, are we talking about means or proportions here? They want to determine the mean number of hours. So we're talking about means here. The sample size formula for means is going to be Z star S E squared. I'll need to find something to plug in for Z star, something to plug in for S, and something to plug in for E. Let's start with E again. E is the margin of error. So what margin of error are we shooting for here? Okay, so once again, I see that phrase within 2 hours. That's telling you how close they want their estimate to be to the true answer. In other words, they're telling you they want to be plus minus 2. So 2 is the margin of error. We're talking about means here, so you don't convert that to a decimal. It's just going to be 2. The next easiest thing here is going to be S. S stands for the standard deviation. Standard deviation, they tell you in the problem, is going to be 7.5. And then Z star. Z star comes from this picture. Area in the middle refers to the confidence level. What confidence level are we shooting for here? 94% confidence, so 0.94. And then we're looking for, I want a Z star. Now, you may be asking, why is it a Z star here and not a T star? Because it is a mean situation. Why is it a Z star and not a T star? And the answer is, if I wanted to find a T star, I would need a left area and a DF, a degrees of freedom, which is going to be the sample size minus 1. So I need a sample size in order to find a T star. But the whole point of this question is to find a sample size. So I can't put a T star there because I don't know the sample size. The next best thing is to put a Z star. So to find a Z star, we're going to be doing Q norm. Left area. To get the left area, I'm going to do 1 minus 0.94. Do 0.06, I believe. That's the unshaded part, left and right together. If I just want the left unshaded part, divide that by 2. 0.03. Okay, that goes into my Q norm. And that's it for Q norm. Q norm doesn't have a DF. Q norm 0.03. Negative 1.881. That refers to the Z star on the left. The one on the right is going to be positive 1.881. And the positive one is the one I'm going to use in my formula. So positive 1.881. Okay, so my final formula is going to be 1.881 times S, which is 7.5, over E, which you said was 2, and then squared. Okay, don't forget the square. Decimals, parentheses, fraction up top, 1.81 times 7.5 over 2, close parentheses, and then square. 49.755. We're talking about sample size here. In other words, how many people we should ask. We can't ask a decimal number of people. So the way you round is to be safe. you're always going to bump it up to the bigger sample size. So bump this up to 50. Example 5. Michael and Lisa are going to construct confidence intervals from the same simple random sample. Michael's confidence interval will have level 90%, and Lisa's will have level 85%. Which confidence interval will have the larger margin of error, or will they both be the same? Remember, there's two things that affect how big or how small the margin of error is, and that's the sample size and the confidence level. Since they're both using the same simple random sample, they're both using the same sample size. So the sample size is not going to affect. What is going to affect who has the larger margin of error is that Michael's is going to be 90% and Lisa's going to be 85%. And remember, confidence level has to do with this picture. Michael's is going to have 90% or 0.90 in the middle, and Lisa is going to have 85% or 0.85 in the middle. So who's going to have a larger margin of error? It's going to be the bigger area, right? 90%. So 90% is going to be the bigger area. Bigger area means that this will be wider. Wider interval means a larger margin of error. So it's going to be the 90%, which is Michael's. Part B, which confidence interval is more likely to contain or catch the true population proportion, or are they both equally likely to do so? We talked about the interpretation of the confidence level in the last lecture, and remember, the confidence level is how likely you are to get an interval that catches your true population proportion or true population mean. So which one is more likely, 90% or 85%? 90%, the bigger one. So Michael again. All right, have a good day, and I will see you guys in the next one.